kind of the extreme programming methodology for development of mathematical models of biological systems, and as example we consider construction of the complex apoptosis model. First of all, some words about this process. Apoptosis is a highly regulated process of the organoid cell death which may occur in multicellular organisms. There are two major pathways of this process: the extrinsic pathway activated via death receptors, including the disk complex formation and the cleavage of space A, and then the intrinsic pathway activated via stress-inducing stimuli, resulting in the cytochrome C release from the mitochondria, formation of the apoptosome complex, and the cleavage of space 9. Both pathways lead to activation of K-space 3, causing DNA fragmentation and cell death. In our laboratory, we developed the modular model of this process based on the mathematical models published in the last 10 years and information collected in the Erectome database. We tried to validate the model using experimental data found in the literature. However, we can do this only for a small part of this data. Thus, we thought about a new concept of modeling based on the principles of extreme programming. Extreme programming, or XP, is a software development methodology based on iterative and incremental development, where requirements and solutions evolve through collaboration between self-organizing and cross-functional teams. Here is a list of techniques which can be applied to modeling of biological systems as well. Firstly, first of all, it's planning, which includes preparation of user stories, just requirements defined by the customer for the final product, then frequent small releases. Just if our product satisfies some new functionality, we release it, and dividing the project into several iterations. That means we divide the current problem into some sub-problems. The next concept is coding, which implies that the code is written in compliance with some standards. And according to this concept, we firstly prepare some unit tests and only then initiate the process of the product development. We often commit code into the code repository, and every project member has a knowledge about every part of the project. And the last concept is testing, including the testing some simple functionality. For this, we use several unit tests, and the testing of functionality required for the customer. For this, we implement some acceptance tests created from the user stories. Here you can see our adaptation of XP to a modeling process. User stories are requirements for the model based on the experimental data we have, and after each iteration, a new set of the experimental data should be reproduced. The standards for modeling are the graphical notation SVGN, the language SBML, and the concept of modular modeling. The model being developed is frequently saved in a public database, and the collective ownership is achieved via collaborative editing and the chat. Also, BioUML provides the facilities for testing the models. Some words about tests. BioUML provides three types of them. These are the steady-state tests, checking whether some variable value is stable or not, the time course test, verifying the deviation between simulated values and experimental dots, and the test controlling whether some value is within the specified bounds or not. And here you can see the implementation of the time course tests as example in BioUML. This is a panel where user should specify the path to the file with experimental data, specify the variable to control, set the maximum deviation to get the test success, and some other specific parameters. Let's turn to a concrete example. Consider a process of apoptosis triggered by some external receptor, for example, CD95 or trail. These receptors induce activation of K-space 9, and after that the execution phase of apoptosis is started. We constructed this phase according to the model of Martin Bentel and his colleagues, and then we prepared some requirements for the model based on experimental data that we had. This data are as follows. If there is no any external signals, then the concentration of the cleaved PARP, the species that detect whether the cell died or survived, is 0. If we consider the apoptosis triggered by CD95, then we must observe the dynamics of procaspase 8 and K-space 8 described by Bentley and his team. And in the case of TNF-alpha signaling, these dynamics must satisfy the data obtained by Janus and his colleagues. Thus, each user story in this example was solved in a single iteration of the modeling process. And each of these iterations was represented by a single test suite, including 1 or 2 acceptance tests in our example. Each test suite characterized by a specific initial state of the model, and each of them could be limited by some period of time, 10 seconds, 20 seconds, and or something like this. So, for the first test suite, our initial model didn't require any changes. Thus, we could run the first test suite. And after running it, we got the success status, and we could also observe the stable dynamics of this species in the plot. When we supplemented the execution phase module by the CD95 signaling, this module was created based on the model of Bentel et al. 2. And for this module, we used the next test suite, and we got the good approximation of simulated experimental dots by simulated data. And in the third iteration, by the same way, we started the next step of the modeling and supplemented the model by TNF-alpha signaling. However, in this example, we didn't finish the iteration because during the new test running, the deviation between the table data and the simulation result was greater than the maximum allowable value. Thus, we need to modify the model to reproduce dynamics of these tests, and iteration will be complete only when all the tests have been passed. Summing up our modeling steps, we obtained the following. Firstly, we considered one execution phase and one test suite for this module. Then we supplemented this module by CD95 signaling and got success results for 2 test suites. And then we added the TNF-alpha signaling and didn't complete the iteration because results of the third test suits were wrong. Anyway, when we finish the third iteration, we will be able to specify the new iterations associated with new modulus and consideration of new experimental data. And thus, the extreme programming methodology implemented to the model process allows to construct the model step by step. Thank you for your attention.